We're going to shift gears as we move into chapter 5. We're not going to do graphing anymore. We're going to go back and talk about identities. If you look in your notes, the first 6 identities listed there are the reciprocal identities. And there's no need to memorize those. Remember, it's just sine and cosecant are reciprocals of one another. Cosine theta, secant theta, reciprocals of one another. Tan theta and cotan theta, reciprocals of one another. The last 2 identities on your notes are the quotient identities. Tangent theta is sine theta over cosine theta, and cotan theta is cosine theta over sine theta. So those we've already talked about. The 3 remaining ones are with the Pythagorean identities. For example, 1 plus tangent squared theta is secant squared theta. And we talked about these before and we proved them, but we haven't really used them very much. Remember what an identity is. An identity is an equation so that any value you plug in for theta, for which every expression is defined, the sides will be equal. So for example, if I plug in theta as pi over 2, tangent of pi over 2 is undefined, 90 degrees. Tangent of 90 degrees, tan of pi over 2 is undefined. But even though that makes this expression undefined, as well as this one, we still consider it an identity, because anything else you plug in for which this left-hand side and the right-hand side gives you a number, they will be equal. So we still consider an equation identity if there are some places where you get undefined. But if you plug in a value here and the same value here and you've got 6 equals 7, it wouldn't be an identity. Now, what we're going to use later in this section is, I have the 3 Pythagorean identities memorized in the way they're printed in your notes. For example, 1 plus tan squared theta, secant squared theta. But you can make new identities from old ones. For example, I know these 2 things, or these 2 expressions are equal to one another. But for example, what if I subtracted 1 from both sides? You get tan squared theta is secant squared theta minus 1. Well, since this is true, you know if you subtract the same quantity from both sides, you still have a valid equation. So this is true. So this is also an identity. Now, I don't memorize this. I memorize the original, and then I can always rearrange, subtract expressions from both sides to make new identities. What if I had subtracted tan squared from both sides from the original one here? Subtracting tan squared, I would have got 1 is secant squared theta minus tan squared theta. So that's another identity. Okay, so you can do this rearranging and make new identities from old ones. So whenever I see an expression with 2 of the 3 things in a Pythagorean identity, a 1 and a tan squared, a 1 and a secant squared, or a secant squared and a tan squared, I think, can I get that from the original identity? And I just do the scratch work to see. So for example, if I saw secant squared theta minus tan squared theta in some sort of problem, I think, wait a minute, that has a secant squared and a tan squared. Can I get that from this? And the answer is yes. So keep that in mind. All your Pythagorean identities are not always going to look like this. Okay, we want to derive some new identities. And so I say, consider the following picture. So I'm going to draw an angle theta in the first quadrant, just like we always did. So suppose I have an angle theta here. I could do this in any quadrant. I'm just going to draw it in the first. And we pick the point x, y on the terminal side of the angle, like we always did. So that's x and that's y, and we call the hypotenuse r. We're going back to stuff we did in the very first chapter. Now, let me consider sine theta, and I'm also going to look at cosine theta simultaneously. So I'm going to do 2 things at once here. Now, what's sine theta? Well, sine is y over r, or opposite over hypotenuse. Sine is y over r. And cosine's adjacent over hypotenuse, or x over r, again, however you memorize those. So this is nothing new. This is stuff we did a long time ago. Well, let me consider the angle negative theta. Again, I've drawn theta as an acute angle in the first quadrant, so negative theta is going to be down here. Right, there's the angle negative theta. And I want to compare the values of sine and cosine, so it would make sense. You can choose any point you want on the terminal side, but if I want to compare, it would make sense to choose the point right here so that I have congruent triangles. Now, what are the coordinates of this point going to be? If this is x, y, where x and y are both positive, the coordinates of this point are going to be x minus y. Again, I've chosen the point here to be congruent triangles, so this is x minus y. And since the triangles are congruent, that's r. Now again, the length of this is y. I'm just saying that I just label it minus y to remind you that your trig functions have the y value here, not necessarily the absolute value. Well, let's find the sine of negative theta and the cosine of negative theta. We have all the sides labeled, so we can do that. What's the sine of negative theta? It's opposite over adjacent, or the y value over the x value. So that's opposite over hypotenuse, so minus y over r. And what's the cosine? The cosine's adjacent over hypotenuse, which is x over r. So we're interested in comparing these values. Well, let's do the easy one first. What's the relationship between cosine theta and cosine negative theta? Well, they're equal. So cosine of negative theta is the same as cosine theta. And again, I drew this angle in the first quadrant, theta minus theta. I could have done it anywhere and you'd get the same result. Okay, so that's one new identity. Now, how are sine theta and sine negative theta, how do those compare? They're not the same. They're off by a minus sign. I'm not saying this one's always negative. Notice that y is negative here, this will be positive here. But they're opposite signs one another. So from this, we get sine of negative theta is the opposite of sine theta. So there's two new identities that we have. So it relates the cosine of an angle and the cosine of the angle is negative, and same for sine. Now I could use this picture to do the other trig functions, but just to show you where we're sort of headed in this section and sections after in chapter 5. Suppose I wanted to derive one for tangent without doing what I've already done. So I'm looking at tangent of negative theta. And I want to relate that to tangent of theta. Well, we know the result right here for sine and cosine of negative theta. Well, so tan of negative theta, if you use the quotient identities, that's sine of negative theta over cosine of negative theta. Right? The quotient identity says tangent of an angle is equal to sine of the angle over cosine of the angle. So whatever angle's here, you put here and here. Doesn't always have to be just a theta. Well, we know what sine of negative theta is. Sine of negative theta is negative sine theta. And cosine of negative theta is the same as cosine theta. So now I have the negative out front, and sine theta over cosine theta is tan of theta. So notice tan of negative theta is negative tan of theta, and it works like sine. If you remember from college algebra, these are odd functions. And cosine's an even function. Well, what if I wanted to do the same thing for cosecant? Well, cosecant of negative theta, well, we know that's 1 over the sine, right? Cosecant, sine are reciprocals. Whatever angle is here goes here. But sine of negative theta is negative sine theta from what we did before. You can pull the negative sign out front, and then what's 1 over sine theta, that's cosecant theta. And notice cosecant of negative theta is minus cosecant theta. Cosecant works the same way that sine and tangent do. And without belaboring the point, you can do it for the others. So cotan of negative theta is just going to be the reciprocals of those, and so you get minus cotan theta. And if I do secant of negative theta, well, secant of negative theta is 1 over cosine of negative theta, which is 1 over cosine theta, which is secant theta. So secant and cosine are the even functions here. So secant and cosine, and the reciprocals, that shouldn't surprise you. Secant and cosine do the same thing, right? Secant of the negative of an angle is the same as secant of the angle. And the other 4, you can pull the negative sign out front. So what is these saying? For example, if I say cosine of negative 20 degrees, that's the same as cosine of 20 degrees. If I do sine of negative 20 degrees, that's the negative of sine of 20, etc. Okay. Now, if you remember in the last chapter, whenever we were doing graphing, when we had a period change in any of the graphs, the coefficient of the angle was always positive. So, for example, we were graphing things like y is 4 cosine 2x, something like that. The coefficient here, the coefficient in front of x was always positive. We had the coefficient of the trig function could be negative. That was a reflection across the x-axis. But what if we had cosine of negative 2x? We never did that before. Well, how would we handle that? Well, we just learned that cosine of the negative of an angle is the same as that. So if we did have a negative coefficient in front of x, you could rewrite it like this and then just go back and do what we did before. What if this had been a sine? A sine of negative 2x, right? We never dealt with the coefficient being negative. Well, what do? According to what we just learned, sine of the negative of an angle is the negative of the sine. Oops. And notice we could graph that just like we did before. Okay. So if we have a negative coefficient of x, for a sine, you can pull the negative out front. We're not going to do that, but that's what you would do in that situation. Okay, so as an example, the next example says simplify the expression secant theta, cotangent theta, sine theta. Now simplify is kind of a subjective term, but we're just going to go with our gut here. So we want to simplify. Well, let me write down the problem here. Secant theta, cotangent theta, sine theta equals. A strategy that often works in simplification problems and identities, which we'll do later, is to write everything in terms of sines and cosines. Notice here we have three different trig functions. If we write everything in terms of sines and cosines, we'll only involve two trig functions, sine and cosine. I'm not saying that's a strategy you always want to use or use first, but often that's a strategy that works. So let me rewrite everything in terms of sines and cosines. So you have to know your identities. Secant is 1 over cosine theta. Cotangent theta, use the quotient identities, that's cosine theta over sine theta. And then sine theta is just sine theta. I'm going to write it as a fraction just because everything else is in terms of a fraction. So secant's 1 over cosine, cotangent's cosine over sine, sine is itself. And notice everything's being multiplied and divided, so you can cancel, everything cancels out and you get 1, which is clearly simplified. So secant theta, cotangent theta, sine theta is equal to 1, as long as everything is defined. So that one's not that difficult, okay? But you have to know, notice what you had to know here, your reciprocals and your quotients, and you had to know how to multiply fractions as well. Well, that wasn't too bad. Now, the next example is an interesting example. In previous editions of this book, this problem was in there. In this edition, they took it out. I think professors across the country probably complained that it didn't make sense. So in terms of the instructions, it really is a stupid problem, but I'm going to do it anyway and give you the answer they expected in the old edition because there's a lot of good algebra in the problem that you can learn from. So it says simplify tan theta plus cotan theta. And I think I'm going to do this problem twice. So try to leave yourself a little bit of room. Or you can always go on the back when we do it again. Okay, so simplify that. I mean, you're just adding two things together. A way to handle this, again, we're going to do this problem two different ways. Well, it's two different trig functions, but they're reciprocals of one another. So we can rewrite this expression in terms of a single trig function. Either take the reciprocal of that or the reciprocal of that. I'm going to take the reciprocal of the second one. So cotangent is 1 over tangent. Again, cotangent theta, whatever angle is here, go here. You don't take the reciprocal of the angle. So now we only have one trig function involved. Well, I want to add these two fractions together, but to add fractions, you need a common denominator. Again, you can think of this tangent as tangent over 1. So they do not have a common denominator, so I cannot add them right now. Well, how do you get a common denominator? Well, the least common denominator, there's a 1 and a tan theta. The product is tan theta. That's the least common denominator. So I have the tan theta here. I don't have to do anything with that, but I need a tan theta here. Now, how do you get a common denominator? I want a tan theta, so you have to multiply by tangent theta over itself, right? I want the tangent theta in the denominator, but you have to multiply by 1 so you don't change the value of the expression. And I still have 1 over tan theta over here. Okay, so that one I didn't do anything with because it already had tan theta. I need a tangent theta in the denominator here, so I multiply by tan theta, but you have to multiply by tan theta over itself to multiply by 1. Now if I multiply fractions, remember multiply fractions, you multiply across, that's tangent squared theta over tan theta. Again, if you write something down you don't like, you erase it, please. Plus 1 over tan theta. Notice I have a tan squared and a tan. Would I want to cancel one of those there? Cancel a tan with a tan square? Well, you could, but there's no point in doing that. You're going to go back to where you started. The whole point was to get a common denominator. You don't want to ruin that. Now that we have a common denominator, I can add the fractions. Remember, to add fractions, you leave the common denominator alone, and then tangent squared plus 1. Okay, tangent squared plus 1. Now you cannot cancel a tan with a tan squared here because everything's not being multiplied and divided. You're adding here. You cannot cancel those. Now there should be something leaping off the board at you right now. Tangent squared plus 1 is one of the expressions in one of the common Pythagorean identities. 1 plus tan squared theta is secant squared theta. And now we've gotten rid of the sum. So if we had a tangent squared and a tangent, we could cancel now, but we don't. Okay, so tangent squared theta plus 1 is secant squared theta. That's one of your Pythagorean identities. And now I think I'm just going to go back to the sines and cosines strategy. Well, secant's 1 over cosine, so that's 1 over cosine squared, right? Secant squared is 1 over cosine squared. And then tangent is sine theta over cosine theta. Now, how do you divide by a fraction? You have a fraction divided by a fraction, you invert the denominator and multiply. So this is 1 over cosine squared theta times invert and multiply, you get cosine theta over sine theta. Now, everything's being multiplied and divided. Something times something divided by something times something. So I can cancel a cosine with a cosine squared, and I get 1 over cosine theta sine theta. Now, cancel a cosine with a cosine squared. And what's 1 over cosine times 1 over sine? Well, there's no point in leaving it as a 1 over because we have names for that. 1 over cosine is secant theta, and 1 over sine is cosecant theta. Okay, now so in the previous edition of this book, that's the answer they wanted you to get here. Now, let me explain to you why I think this is a silly problem, and I'm sure others did too. We started with the sum of two trig functions, and the instructions said to simplify. And the answer they wanted was the product of two trig functions. Why is that simpler? It's not. The sum of two trig functions and the product of two trig functions, this is not any simpler than that. So that's why they got rid of the problem, because the instructions didn't make any sense. But I like doing this for you anyway, because look at everything that's involved in this problem. What did we use? I used a reciprocal identity. I got a common denominator. I used a Pythagorean identity. I changed the sines and cosines. I divided fractions, and then I used reciprocal identities again. There's a lot of good stuff in this problem, even though the problem overall, the instructions are stupid. Okay? So I like this problem because there's a lot in it that you're going to use in this section. Now let's do the problem again using a different approach. Now a lot of the elements we used are going to be the same. And I'm still going to try to get down to that answer, which is what they wanted in the old edition. But instead of changing to tangents, I'm going to use the strategy of changing everything to sines and cosines in the first step. Okay, so let me start with my original expression, tan theta plus cotan theta. Okay. If I change everything to sines and cosines, well, tangent is sine theta over cosine theta, and cotangent theta is cosine theta over sine theta. I'm going to follow the same procedure I did before. I need a common denominator. Now, I have a cosine theta here and a sine theta here. The least common denominator is the product of those sine theta, cosine theta. So I need a sine theta in this denominator. I need a cosine theta in that denominator. So I need to multiply by something over itself to get the common denominator. So I need I'm trying to get sine theta, cosine theta. I have a cosine theta, so I need a sine theta here. But you can't just multiply by sine. You have to multiply by sine over itself to multiply by 1. Because 1 times that doesn't change the value. We'll change the appearance, but not the value. Here I have a sine theta. I need a cosine theta in the denominator. And again, I need to put cosine theta over itself. Because that times 1 will still be that. I'll change the appearance, but not the value. So what do we have? If I multiply the fractions, I get sine squared theta over sine theta cosine theta. Here, if I multiply the fractions, I get cosine squared theta over sine theta cosine theta. So now I have my common denominator. I can add the fractions. When you add the fractions, you leave the common denominator alone. And I add the fractions, I get sine squared theta plus cosine squared theta. Well, again, that should leap out at you. That's part of a Pythagorean identity. Sine squared theta plus cosine squared theta is always 1. So the numerator turns into 1. And notice we're back to where we were at the very end of the same problem. We just did 1 over sine is cosecant theta, 1 over cosine is secant theta. So we got the same answer. Now what do we use here? We change everything to sines and cosines. Notice we did that at the very end of the last method we used. Here we did it at the beginning. Got a common denominator, used a Pythagorean identity, and took reciprocals. So we used everything we used before, we just did it in a different order. Okay? So that's that one. Again, the instructions are silly on that one because we didn't really simplify. Okay, so on the next page, we just have several examples to do of this same type, just trying to simplify. It says simplify sine theta times cosecant theta minus sine theta. So think for a second what you might consider doing first on this problem. I mean, a lot of times when it's simplifying, there's more than one way to begin. It's just a matter of which way appeals to you. So again, let me write down the expression. Always write down what you're starting with. I can think of two reasonable things to start with. Either distribute, which is perfectly reasonable, or we have two different trig functions here, sine and cosecant. Maybe change cosecants to sine, and then you only have one trig function. Okay? Either one's reasonable, perfectly fine. Whatever you do in the first step, the other one you're going to do in the second step. I'll just distribute, just to do something. So if I distribute, I get sine theta cosecant theta minus sine squared theta. I know that looks worse. Sometimes it looks worse before it actually simplifies. Okay, now I'm going to change the cosecant in terms of sines. Cosecant is 1 over sine. Remember, you have to know your identities. And the sine squared theta stays alone. Stays the same. And well, what's sine times 1 over sine? Right? Sine times 1 over sine is 1. Right? Think of that as sine over 1, the sines cancel, and you're left with 1. So 1 minus sine squared. Now that's not the end of the problem. As I mentioned at the beginning of the section, I have a 1 and I have a sine squared in this expression. That makes me think Pythagorean identity. We have a Pythagorean identity that has 2 of those elements in it. So as scratch work over here, my thinking is, let me write down the identity I know. Sine squared theta plus cosine squared theta is 1. That's the one I have memorized. What can I do to this identity to make one side look like this? Well, if I subtract sine squared from both sides of that, if I subtract sine squared from the left, I'm left with cosine squared. Now I subtract sine squared from the right, I'm left with that. So this identity is true, I've made a new identity from it. 1 minus sine squared is cosine squared. So 1 minus sine squared is cosine squared, which is simpler. This is a trig function squared, that's a trig function squared, but this is 1 minus that trig function squared. So this is simpler. And you can't get much simpler than the power of a trig function. So a lot of these problems where they say something, you just go with your gut. You're not going to see 8 steps ahead. Try something. See if it goes anywhere. If it doesn't, you start over and try something else. Students will always ask me, how'd you even know where to begin? I don't know. Because I've done 1,000 of these. Right? You get better at it with practice. So just staring at it, not trying anything is not going to get you very far. You have to try something. Sometimes you just try and you don't even know what you're doing, and then you're all of a sudden, oh, look, it pops right on out. But you just have to try something. Okay, the next one is similar. It says simplify secant theta plus cosecant theta times cosine theta minus sine theta. Okay, let me write down the problem again, what I'm trying to simplify. Secant theta plus cosecant theta times cosine theta minus sine theta. This is what you need to be doing in your homework. Always write down what you're starting with. Again, can you think of something that's reasonable to start with here? Well, I can think of 2 things again. Either multiply the whole thing out, or I have 4 different trig functions here. If I change everything to sines and cosines, you only have 2. Why don't I go ahead and do that first? So secant theta is 1 over cosine theta. Cosecant theta is 1 over sine theta. And I'm left with cosine minus sine. I'm not going to touch that. So everything's in terms of sines and cosines. I mean, if you wanted to multiply out first, that'd be fine too, but I think your second step is going to change everything to sines and cosines. Now let me multiply this out. So if you FOIL, 1 over cosine times cosine is 1. Right? Think of this as cosine over 1, the cosines cancel, you're left with 1. And if I do that to the outside, you get minus, think of these as over 1. Sine over 1 times 1 over cosine is minus sine over cosine. And then 1 over sine times cosine over 1, that's plus cosine theta over sine theta. And then if I do that times that, it's a minus times a plus, minus. 1 over sine times sine over 1, well that's sine over sine, which is 1. Okay. So notice what happens here. I get a 1 minus a 1, that's 0, that's gone. Well, what's sine over cosine? Sine over cosine is tangent, and cosine over sine is cosine. And that's the answer they want on this problem. You could actually do what we did before on that problem that I said was silly. You know, subtract these 2 and maybe work it down to something else, but a product. But a product, again, is not simpler than a sum, so. That's the answer they want on this problem. Okay, the next problem. Let me caution you on the next problem. In the homework, this is from the homework set, the instructions say, first change everything to sines and cosines. I want to caution you, that is not always the smart thing to do on the first step. This says simplify 1 minus tan squared theta over 1 plus cotan squared theta. Okay, again, the instructions in the homework say, write in terms of sines and cosines first. You don't always want to do that first. In this problem, it's silly to do that first. It makes it a big mess. Okay, so in that set of problems where they say change everything to sines and cosines first, you don't have to do that. You may want to do it eventually, but you don't want to do it first. What should you do first here to simplify? Goodness gracious. 1 plus tangent squared is directly from one of our Pythagorean identities. So is 1 plus cotangent squared. So that you don't even have to do that rearranging stuff that I did a little while ago, trying to get a new identity from an old Pythagorean identity. 1 plus tangent squared theta is secant squared theta. That's directly from a Pythagorean identity. 1 plus cotangent squared theta is cosecant squared theta. It's directly from a Pythagorean identity. That's why it's silly to change the sines and cosines. Think about what this would look like if you did that. 1 plus sine squared over cosine squared over 1 plus cosine squared over sine squared. What a mess. It's easier just to use the Pythagorean identities on this problem first. Now I think it's reasonable to change the sines and cosines, because I don't know what else you would do here. Secant squared theta is 1 over cosine squared theta, and cosecant squared is 1 over sine squared theta. And notice I have a fraction over fraction. How do you divide fractions? You invert the denominator and multiply. So I'm going to invert the denominator. You get sine squared theta over 1. So notice when I multiply, I get sine squared theta over cosine squared theta. Remember, sine over cosine, the quotient identity says sine over cosine is tangent. And so sine squared over cosine squared is tangent squared. And there you go. So again, changing everything to sines and cosines is not a good strategy to start this problem. Once I use the Pythagorean identities, then it makes sense to do. So that one's really not that bad either. But what we use here, Pythagorean identities, change the sines and cosines, quotient identity. Notice I keep using the same strategies over and over and over again in these problems. In the previous two problems, change the sines and cosines, Pythagorean identities, and multiply. Right? Use distributive law and we foiled in the second. And then the last problem in the notes for this section says simplify tan of negative theta over secant theta. Now, can you look at this problem and see what's a little bit different about it from problems we've already been doing? Well, one main difference is the angles are not the same. All the problems we've done up to this point in this section, it always said theta, 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 theta. Every angle is theta. Notice here we have the angle here is theta, but the angle in the numerator is negative theta. They're not the same angle. And if you want to use Pythagorean identities, for example, it's sine squared theta plus cosine squared theta equals 1. The angles have to be the same. They don't have to be theta, they just have to be the same. Same with the quotient identities. Tan of theta is sine of theta over cosine theta. If you want to use the quotient identities, all the angles have to be the same. So before I will do anything here, I want to make the angles the same. Remember back to the very beginning, we proved some identities for the 6 trig functions of sine of negative theta, cosine negative theta. Tan of negative theta, if you remember, was the negative of tan theta. So I can pull the negative out front as a coefficient. And the only reason to do that is now I have the angles matching. That was the only point of that. Now I think changing the sines and cosines, so tangent is sine theta over cosine theta over, and then secant theta is 1 over cosine theta. So again, that's one of the new identity. That's a quotient identity, that's a reciprocal identity. And to divide by a fraction, I'm copying the numerator here. To divide by a fraction, you invert and multiply. So I get cosine theta over 1. Everything's being multiplied and divided, so I can cancel the cosine. And you're just left with minus the sign. So again, what did I use here? I use the new identity, quotient identity, reciprocal, multiplying fractions, and cancel. So I keep using the same ideas over and over and over again on all these problems. So you should probably stick to some of these same ideas. Again, you have to try something first. If you get a mess and try something else. Okay, you're not going to get all these right on the first try. And you also cannot start these 5 minutes before the homework is due. You have to start these days before it's due, week before it's due. Try some. You'll get some, you won't get some, and then go back to the ones you couldn't get. Okay, you're not going to be able to do all this homework in 5 minutes. You have to start early and give yourself lots of time to practice.